let's talk about a heat pump. Alright, so the idea of a heat pump. This is a refrigerator, as we've just discussed, an object that moves heat, cools down a low temperature body by taking work in and putting all of that energy then out to a higher temperature body. Now, a heat pump does the exact same thing. A heat pump is what I would call a repurposed refrigerator. The same exact device is going to have a compressor that pushes high pressure, high temperature fluid into a condenser, and that's where you're going to lose heat to the high temperature body. And the purpose of the heat pump is this is what you want to do, is you actually want to add heat to the high temperature body. And again, to do that, you're going to have to put work into a compressor, and then it's going to go through some kind of expansion process, probably an expansion valve, and then you're going to have heat going into some evaporator coils coming from some kind of low temperature body. So it's the exact same layout device that we see in a refrigerator. The difference is what you want, your COP for a heat pump, because your goal for a heat pump is to actually heat the higher temperature body by cooling the lower temperature body. Right, that's going to be our goal there. To do that, you're going to have to put work in. Right, so that's the denominator in our coefficient of performance. And again, if I plug in, it's the same first law. Right? First law of work in is equal to QH minus QL. That's the same first law that we had for a refrigerator. If I plug that in here, this becomes 1 over 1 minus QL over QH. And again, if I'm operating in a Carnot cycle or any other reversible cycle, this device operates at its highest performance, which we can calculate by 1 over 1 minus TL over TH. Now, again, just like with a refrigerator, we do not call this an efficiency because this value can exceed 1. And in fact, in a heat pump, this value does exceed 1, right? This value, the QH is always larger than the work in. Always. Always, always, always. How do we know that? Well, because QH is equal to work in plus QL. These two combine to form QH. So QH is always greater than the work in. Coefficient of performance for a heat pump is always greater than 1. So that's the reason we call it a coefficient, not an efficiency. Anything that can exceed 1 is not a true efficiency. However, a COP, again, just like over here, needs to be a unitless quantity. You need the same units on top and bottom. Okay? And again, this represents the maximum coefficient of performance for this device. I think, looking back at my notes over here, I think that gets us, that's the major topics we've got to talk about in Chapter 6. I think that brings us then to Chapter 7. In our text, again, Chapter 6 kind of introduces the first law without ever actually doing anything useful or quantifying, well, I won't say anything useful, without ever actually showing you the second law. So if we talk about Chapter 7 in our text, that is the second law and entropy. Okay, so we talk about the second law and entropy. Our good friend Clausius came to the realization that a change in entropy is always going to be greater than or equal to the heat transfer that causes it divided by temperature. Now, this was not actually his conclusion. His conclusion was that if you have a cycle right? That for a cycle, the change in entropy is going to be 0, but what he found is that if you went across the entire cycle and added up everywhere heat transfer occurs, this being a cyclic integral, so everywhere heat transfer occurs across the entire cycle, divided by the temperature at which it occurs, this always represents a negative quantity, right? So this is always less than 0. As you approach reversible, as you increase your efficiency, if it's a heat engine, as you increase the efficiency for this device, you approach closer and closer to reversible. You could approach 0 for this quantity, but you can never actually get there. You're always getting a negative quantity. I apologize. Let me put this on mute. You're always getting a negative quantity here. And what the conclusion then is, this is actually measuring some property, something that we could measure. And what we've decided upon is that this represents entropy. So what happens, the entropy is your disorder, your chaos, the unpredictability of the molecules within the system. We can increase or decrease the unpredictability of the motion or behavior of those molecules by removing heat or adding heat. So as I add heat, I increase entropy. And that increase is based on the temperature at which I add the heat or remove the heat. And what we find is that the amount of entropy change is always greater than the amount of heat required to change the entropy. Now, this raw differential inequality is, we're not necessarily going to use this. Again, I'm not assuming you've had differential equations yet. Let's get this down to something that's a little more palatable, if you will, something that's a little easier to use, for maybe some kind of an algebraic expression for a process from state 1 to 2. Again, this is the second law in its raw differential inequality form. If I integrate both sides of this inequality and I change it to an equation, I can do that. If I integrate this for a process from state 1 to 2, these are big S's. Total entropy change, big S's, is going to equal the integral from state 1 to 2 of this dq over T, all of the heat transfer occurring from state 1 to 2, divided by temperature, plus the amount of entropy generated. Okay? Now, do I have something that, maybe I've got a picture of something or some kind of system that I can do this for, right? If I can analyze what this looks like. Well, if you think about, there we go. We put this in terms of a heat engine. And if I say, well, let's say that this is, going into the turbine is state 1. We go around the cycle, and coming out of the boiler then we'll say is state 2. So the entropy change from here to here, again, this is a cycle. We've already said the internal energy change is 0 for a cycle. Same thing with the entropy. The water gets, the working fluid, typically water, gets back to the same state as it goes around the cycle. So for a cycle, for a heat engine, let's say, for a heat engine, S2 is going to equal S1. And let's say for a heat engine that's reversible, Carnot or otherwise, well, S2 is equal to S1, and if it's reversible, the entropy generated is 0. All right? So if it's a cycle, I'm going to have an entropy change of 0, and I'm going to generate 0 entropy. So all I'm left with is this integral of dq over T plus the entropy generated is 0. All right, well, if we go around this heat engine cycle and we say, all right, well, everywhere that I add heat, I need to add Q divided by the temperature at which it occurs. So again, 0 for the cycle, entropy change for the cycle. And then let's expand on this integral here. So everywhere around this cycle that I add heat, I'm going to add that heat. That's what this integral is telling me, is add the heat in divided by the temperature at which it occurs. And everywhere that heat goes out, subtract the heat divided by the temperature at which that heat occurs. So here I'm losing heat at TL. And then to satisfy the second law, I've got to add the entropy generated. Well, if it's reversible, that's 0. So therefore, QH over TH is equal to QL over TL, or QH over QL is equal to TH over TL. Now that's if we assume the second law is true. If we assume the second law is true and it works the way we think it does, for a reversible process, for a reversible cycle, the ratio of heat transfers is equal to the ratio of temperatures. And that's why we know this is the thermal efficiency for my heat engine. And Carnot tells us if it's a reversible cycle, the ratios, well, the only thing that controls this efficiency is the temperatures at which you exchange heat. And this is the proof, assuming we assume the second law is correct, that this is the maximum efficiency we can achieve with a heat engine is based off the ratio of temperatures. Again, I'm not saying this temperature and this heat are the same. I'm saying the ratio of the heat is equal to the ratio of the temperatures if it's reversible. Okay? Kind of important concept there. Now, if we go back to this second law, this is kind of the most common form of the second law that we could use, because it's pretty common that we'll deal with a process from state 1 to state 2. So if we look at, again, repeating, for a process from state 1 to 2, I'm just going to repeat what I had over there. That means big S2 minus big S1 is equal to the integral from 1 to 2 of d big Q over T plus big S gen. If you work per unit mass, that means little s2 minus little s1 is equal to the integral of d little q over t plus little s gen. All of those are per unit mass. And if I multiply everything by m dot, that's m dot times little s2 minus little s1 quantity is equal to the integral from 1 to 2 of d big Q dot over t plus big S gen dot. These are all rates. All these terms are entropy rates. Energy. So this is total entropy, energy per temperature. Every one of these terms is energy per temperature. Every one of these terms is energy per temperature per mass, and every one of these terms is energy per temperature per time. They're all the same equation. Use them interchangeably. We've seen these before. Again, this is kind of a review. Again, what we've done to make this, where we started out with an inequality, to turn it into an equation, I'm saying that this entropy change is greater than the heat transfer that causes the entropy change. The amount that it's greater than is the entropy generated. If S gen is greater than 0, then that's normal. We call that irreversible. That's what we expect. If S gen is equal to 0, that's reversible. That's the best version of the device or process. Now, a lot of people will get stuck on looking for max or min. That's not what you're looking for. You're looking for, is it something like the maximum output? If it's a turbine, the purpose of the turbine is to get output. The best version of the turbine has the maximum output. The compressor is going to be the minimum input. You don't want the compressor with the maximum input. That doesn't make sense. You don't want the turbine with the minimum input. The minimum output. You don't want a turbine with the minimum output. That doesn't make us rich. That doesn't help us. Don't get stuck on max or min. Think about the purpose of the device. And I think I can say quickly here that S gen negative, we do not believe we can destroy entropy. We believe that it is impossible to destroy entropy or have negative entropy generation. We'll pick up there.